Logistic regression is another supervised learning algorithm, and it falls in the category of classification. So the other algorithms that we have already looked at that fall in the classification domain are decision trees, naive Bayes, KNN. So today we're also going to look at the logistic regression, which also is a classification problem. The last week and today's lecture, the previous lecture also, we were looking at linear regression. And again, just to summarize, the difference is between the classification and regression. The difference is in classification, Y is discrete. And more specifically, we will be considering a binary classification problem, which means Y will either be 1 or 0. Okay? And linear regression, Y belongs to any real value, any continuous value. So logistic regression is a classification problem, and the idea is to see whether we can apply the procedure or to apply linear regression framework to the classification problem, and what we need to modify in order to successfully apply the linear regression framework to classification. Some examples of classification, of actually binary classification. So if we want to, based on the email text, if we want to classify the email into spam, not spam, this is a classification problem, binary classification. Online transaction is fraudulent or not, yes, no, is again a binary classification problem. Similarly, a tumor is malignant or benign is again a binary classification problem. And so as I mentioned before, it can have either 0 or 1 value. Now let's apply linear regression technique to classification, okay? Which means that if I have a data set like this, X is the size of tumor, and Y is my prediction, and I have examples. For example, this is size 1, 2, 3, 4, 5, 6, 7, 8. I'm just giving the example. If the size of the tumor is 1, then it is malignant, it is benign. Size is 2 is 0, size 3 is 0, size 4, 0, 5, 1, 6, 1, 7, 1, and 8, 1. So these are my 8 examples. So the first 4 are here, which are benign, and the next 4 are malignant. If I plot them, this is the plot I get. If I apply linear regression, what we did in the previous lecture, then I expect to get a line like this. Joyan drawn, and let me also draw in the same color. So I expect to get a line like this, right? Because linear regression is going to output a line. What this line is telling me, if I now want to find the prediction, what is whether I have tumor or not, and I say, okay, the size is, let's say, 4.5. Then it's going to maybe see over here, it lies over here, and it's going to tell me, okay, this is the value, maybe 0.3 or something like that, or 0.4. Similarly, if I say 5, then it's going to give me the value, some value, some numeric value. Because it's regression, it will be a continuous value. So ultimately, I will have to then apply some kind of threshold. For example, if I can say that if h of x is greater than 0.5, which is something here, then I will say, okay, this belongs to class 1. If h of x is less than or equal to 0.5, I will say this belongs to class 0. So I will have to apply some thresholding after applying the linear regression. So far so good. But if I have another example, which is this example here. Now if I apply the linear regression problem, then of course the output line, the prediction will change. Now the prediction would be something like this. And in this case, if I apply the same threshold, which is 0.5, then you can easily see that that threshold will be wrong now. ठीक है, वो तो आपको इन दो को भी वो कह रही है कि ये ये prediction ये बता रहा है कि आपको this is also 0 but they are 1, you know, from the training examples. So what you need to do is to modify your threshold. Given a new example, you have to then adjust the threshold again. Maybe in this case you set the threshold 0.2 somewhere here. If the prediction is greater than 0.2, you have y1, otherwise it is 0. So what I am trying to say here is that the linear regression you cannot directly apply. You have to apply some threshold, and then you have to adjust the values of the threshold. The second important thing is that the value of the prediction can be greater than 1. It can also be less than 0. Essentially, it can be any value. It can even give you, you know, infinity. I mean, giving you example, any large value. Similarly, the prediction can also be some very small value. There is nothing in the linear regression which stops, you know, your prediction from going over there. For example, if I have tumor size is lies somewhere over here, then, you know, looking at the line, I will have a value which is greater than 1. But I know that the ground truth only belongs to 0 and 1. But in the linear regression framework, the hypothesis is framed in such a way that there is no constraint or there is no restriction which will avoid getting the values bigger than 1 or less than 0. So what do we need to change? We need to change the hypothesis. Okay, we want a hypothesis which gives us value between 0 and 1. Why? Because we know the ground truth value is either 0 or 1. Okay? So the number one thing that we are going to change in the linear regression is the hypothesis. So we are going to change the hypothesis in such a way that we will get values between 0 and 1. हम ये चाहते हैं कि हमारा जो ऐसा हाइपोथेसिस हो कि जो 0 और 1 के दरमियान वैल्यूज दे. So hypothesis representation. So how will we now do this representation? So so what we are essentially going to do is to apply some function which over the you know, this theta transpose x, which is the hypothesis for the linear regression. We are going to still use this, but we're going to apply some function over this output so that that function should be able to squash the value between 0 and 1. So that this is what I'm talking about. Let's plot the values theta transpose x. Let's say on x-axis I have the value theta transpose x. So linear regression does not stop the value from getting bigger than 1 or less than 0 on any value. So I have, you know, so this x-axis basically goes from, let's say, minus
उससे पता
infinity.
क्या किया पहले जो एसएल को स्लाइड.
So this goes from minus infinity to plus infinity. Okay. Now what do I want to do? What I want to do is that I want a graph like this. Let me change the color. Okay, if theta transpose x has a value which is negative, then I get all around 0. If theta transpose x has a larger value, then I get approximately 1. In between, you know, in the area around this region, I get the value of the output increases. At 0, it becomes 0.5, and then, you know, it slowly converges to 1. So this is what I want. So if I have this function, let me call this function g. If I have this function, then no matter what theta transpose x is, the output will always be between 0 and 1. Okay. So this is what I want. Okay, I will pass this output to a function g, which is of a shape like this कि आपके पास अगर वैल्यू नेगेटिव है, you know, maybe let's say कि -4 से कम वैल्यू, it is less than -4, you get approximately 0. Similarly, if the value is greater than around 4, you get approximately 1. In the values between -4 and 4, it is going to slowly rise and converge till 1. And exactly at 0, it is going to be 0.5. So what is this function that gives me a shape like this? This function, let me first write its equation. This is this function. If you plot this function for different values of theta transpose x, you will actually get this function here. Okay, this function is called sigmoid, or this function is called logistic function, and that is why the name of the topic is also logistic regression, because we are using the logistic function. This function is also called sigmoid. And so usually you will also see this sign instead of G, but I mean G is not used actually. This sign, this symbol is used. This is sigma symbol. So this is what we are going to do. We will use this hypothesis, linear hypothesis, that we had in the case of linear regression, but we are going to apply a sigmoid function to that linear hypothesis, and the result would be a shape like that, values less than -4 are going to get 0, values greater than 4 are going to get 1, intermediate values will be like this. You can slowly rise and then go to 1. Okay, any question? Okay, so what is the interpretation of this hypothesis? So my hypothesis is now this sigmoid function or logistic function, or you can, for this lecture we can also call it G, doesn't matter. Theta transpose x. So this is my hypothesis function. I know it will always be between 0 and 1, because the way the sigmoid function is, it's always going to be between 0 and 1. So what we can say about hypothesis is that this basically is a probability. Okay, it is estimating the probability of x belonging to the class y is equal to 1. So for example, if h of x comes to 0.7, so I'm going to say that 70% chance that this x belongs to class 1. And since there are only two classes, so the remaining 0.3 or 30% is the probability that it belongs to class 0. So this is how we are going to interpret the output of a logistic regression. We will assume that it represents a probability of the x getting a value 1 or 0, or belonging to the class 1 or 0. ठीक है? And yeah, so this is how we write basically the output. This h of x, we are going to assume that this represents the probability that y is 1 conditioned on the parameter that you have. So this is what is the interpretation of the hypothesis function. So this is a probability that y is 1. And similarly, if we want to compute the probability that y is 0, we simply subtract this value from 1. Okay, we have looked at the interpretation that it is a probability. Let's now look at the geometric interpretation of the hypothesis function. Okay, geometric and what is the spelling of interpretation? interpretation of h of x for the logistic regression. Basically, we want to see how does it divides uh, the the space in which our input points live, because ultimately, we are separating using a linear decision boundary our space into two parts, one class and the second class. For example, if this is my data, where this is the first feature, this is the second feature. I'm not talking about data set in which I have two features, and if I have two classes, for example, this is one class, data set from one class, and similarly I have a data set from another class which is here. So this hypothesis, it's going to give me some boundary, some lines. Again, since we are in the linear domain, we have not changed that. So this will give us a linear boundary which is going to separate one class from the other. So everything that lies to one side of this decision boundary would be one class. Everything that lies on the other side would be the other class. We will see how this geometric interpretation or how this decision boundary is formed uh, if we know the parameters. Okay, so this is my decision. This is the output, the shape of the output, right? So when is h of x equals to 0? When is it equal to, sorry, when is it equal to 0.5? When this is equal to 0.5? Because this is the question.
0.
Okay. When theta transpose x is 0. Okay, when this z is basically theta transpose x. So when theta transpose x is 0, you get 0.5. If theta transpose x is greater than 0, your prediction would be greater than 0.5. If theta transpose x is less than 0, your prediction would be less than 0. So यहाँ तक तो बात ठीक है, समझ आ गई कि it depend your this जो sigmoid function जो g है, it will be 0.5 when this argument, this theta transpose x is 0. And if theta transpose x is greater than 0, it will be greater than 0.5. The maximum value will be 1, but greater than 0.5. So let's see ke when will theta transpose x is 0, because that is the, remember, we are assuming that this is a probability. So when this is the probability, so anything greater than 0.5 belongs to one class, anything less than 0.5 will belong to another class. So if we have two classes 0 and 1, so the probability of 0.7 or anything greater than 0.5 means that it belongs to class 1. Anything less than 0.5 will means belong to class 0. But if the probability is 0.5, it means that we lie at the boundary. Okay. So when is the probability 0.5? When theta transpose x is equal to 0. So that will define the decision boundary. कि वो बाउंड्री जहाँ जो आपके प्लेन को या आपके स्पेस को पार्टीशन कर रही है दो हिस्सों में, एक तरफ एक क्लास है, दूसरी तरफ दूसरी क्लास है. Okay. So let's say again, let's take the example of a two-dimensional space. ये आपका feature 1 है, ये आपका feature 2 है. ठीक है. तो yeah, in general you have a, an Euclidean space like this, and you have two vectors. ये vector A है, ये vector B है. So when so A will is a two-dimensional vector. Similarly, B is also a two-dimensional vector. ठीक है. some value here, some value here. If you take the dot product is simply A transpose B, right? And it is also equal to the A magnitude B magnitude cos थीटा. ठीक है, ये तो आपने पढ़ा होगा कि डॉट प्रोडक्ट बिटवीन टू वेक्टर्स इज इक्वल टू ए बी cos theta. So the question is, when will this dot product equal to 0? क्योंकि यहाँ हम वही बात कर रहे हैं कि this is also a dot product between two vectors between theta and x. तो हम वो चीज़ डिस्कस कर रहे हैं कि when this is equal to 0, that is why we are studying here कि when will the dot product between two vectors, any two vectors a and b, is equal to 0.
So angle
So when
90
theta is
degree.
equal to 90 degree.
ठीक है, करेक्ट आंसर के a and b these are magnitude, तो ये तो 0 नहीं होंगे. We have some non zero vector. तो it will only happen कि जब थीटा आपका 90 है. It means कि अगर हम a को देखें तो a के साथ वो सब वेक्टर्स जो कि एंगल 90 बना रहे हैं, they lie on this line here, on a line which is perpendicular. This is a line which is perpendicular to a. तो any vector, let's say कि ये वेक्टर हम ले लेते हैं, this vector making a 90 degree angle, so a dot with this blue vector would be 0, or you may take this vector here, or this vector here, or a smaller vector here. So all these vectors are making a 90 degree angle, and they will give us a 0 magnitude, a 0 value. So when will the probability or hypothesis be 0.5? Whenever theta transpose x is 0, which means whenever theta and x are at 90 degree angle with each other. So let's look at an example. This is your training set 2 0, 0 2 and 2 4. This is x1, this is x2. Let's look at the first example 2 0. This is the plot 2 0. ठीक है, ये मैंने यहाँ plot कर दिया 2 0. 0 2 is here and 2 4 is here. Okay, and let's say कि you are given the parameter. So let's assume again, just for the sake of simplicity, कि आपका जो bias term it is not there, it is 0. We are just ignoring that. So you just have 2 minus 1. So let's also plot 2 minus 1, this parameter vector. So this is my parameter vector theta, which is 2 minus 1. So where will the decision boundary lie? कि decision boundary का मतलब ये है कि when theta transpose is x, so at what x will my theta transpose x be 0? At a line which is perpendicular to theta. So this is the line that I have drawn, which is perpendicular to theta. Any point x that lies on this point will have 90 degree angle with my theta parameter, and so it will give me 0 value. When it is giving me 0 value, then the prediction would be 0.5 k. This exactly lies on the boundary, so my probability estimate is 0.5. Anything that lies on this side will make what angle? Acute or obtuse?
Acute.
So acute angle, so cos of theta when theta is less than 90 is always positive. So this is always going to create a positive value of theta transpose x. And this I know, okay, if theta transpose x is greater than 0 or positive, it means that my prediction would always be greater than 0.5. ठीक है, क्योंकि remember that this is your logistic function. कि एग्जैक्टली 0 पे वो 0.5 है, और 0.5 से अगर आपकी थीटा ट्रांसपोज x की बिगर वैल्यू है, तो योर प्रेडिक्शन वुड बी ग्रेटर देन 0.5. एनीथिंग दैट लाइज ऑन दिस साइड वुड मेक एन एंगल ऑब्ट्यूस एंगल. obtuse means greater than 90, and greater than 90 cos theta is always negative. So if theta transpose is negative, then my prediction will always be less than 0.5. So anything that lies on this side would be assigned a class 0, क्योंकि वो उसकी वैल्यू 0.5 से prediction कम आ रही है probability. Anything that lies over here will be assigned class 1, क्योंकि that is on the that value is greater than 0.5. And this line over here, this line, this is the decision boundary. Okay, so this is the geometric interpretation of your hypothesis function. In a simple case, जब आपके पास दो जो features are two dimensional या दो ही features हैं आपके x में, multiple features हैं, तीन features हैं, no problem, you will have third feature here, but then you will have a plane, not a line but a plane separating the boundary. So उस case में you will get a plane. In higher dimensions, you will again get a hyperplane in higher dimension, but it will still be a plane, a flat thing. Okay, क्योंकि हम we are still talking about linear, not non-linear decision boundary. So your decision boundary will be linear. It will be perpendicular to the parameter vector, because only then you will get a zero value of theta transpose x. Okay. So for example, now the question is, for example, this is my ground truth. This is 1, this is 1, this is 0. Okay. So I have two options now for my theta. So this is, let's say ये मैं नहीं पता, मैं ये पता है कि हमारे पास दो options हैं. एक ये है कि I have, this is one option of theta, ठीक है, and this is the other option. Let me draw with purple. This is the other option. Okay. तो इसको हम ignore कर दें वाले को. And this, so for both of these theta parameters, the decision boundary is this one. कि उन दोनों के perpendicular है ये. By looking at your training examples, can you tell me which of these two theta parameters will give me the right prediction? Okay, I reiterate the question. This is my training example. 2, 0 is 0, which means that this is 0. It belongs to 0 class. This belongs to 1 class. This also belongs to 1 class. Okay. I have given you two theta parameters, the yellow one and the purple one, and corresponding to both of these I have the decision boundary which is shown here. ठीक है. Now the question is कि इन दोनों में से कौन सा आपको जो थीटा है वो आपको करेक्ट प्रेडिक्शन देगा. करेक्ट मीन्स कि जब आप थीटा h of x to 0 करेंगे तो it's going to give you 0, or it's going to give you the probability which is less than 0.5. So क्या जब करेंगे to 0 तो it should give me the probability less than 0.5. Similarly जब आप पास करेंगे 0 to, तो it should give me probability greater than 0.5, and similarly for 2, 4 as well, greater than 0.5. तो which one of these hypotheses, the yellow or the blue one, कि आपको ये इस तरह की prediction देगा? Okay, एक आप कहा कि blue one. The reason for that?
सर उसका थीटा 90 से बड़ा है तो उसका cos थीटा नेगेटिव होगा, तो जो 1 वाली साइड है वो 0 से कम होनी चाहिए.
Let's look at the blue one. ठीक है, जो आपने कहा. अब blue one ये है, और कौन सी साइड इस decision boundary के is going to make an acute angle?
तो 0.
ये साइड आपकी जितनी भी है, ये साइड है, ये इस पे कोई भी पॉइंट लाई करता है, इट इज गोइंग टू मेक एन एक्यूट एंगल विद दिस। ये अगर पॉइंट है तो दिस इज ऑल्सो मेकिंग एन एक्यूट एंगल कम लेस देन 90। व्हेन इट इज मेकिंग अ लेस देन 90 एंगल, तो आपका जो थीटा ट्रांसपोज एक्स है उसकी वैल्यू 0 से बड़ी होगी, 0 से कम होगी?
0 से बड़ी होगी।
It will be greater than 0. When this is greater than 0, what will be your prediction then? आपकी prediction क्या होगी? ठीक है, रिमेंबर ये आपका प्रिडिक्शन वाला जो है ना, जो लॉजिस्टिक फंक्शन है वो ये है कि ग्रेटर देन 0.5 से इट इज गोइंग टू गेट एज थीटा ट्रांसपोज एक्स बिकम्स ग्रेटर देन 0, वो वैल्यू आपकी बढ़ रही है, 0.5 से बढ़ रही है। और थीटा जब आपका, लेट मी ड्रॉ इट इन क्लियरली, x-axis पे you have theta transpose x exactly at 0 value of theta transpose x you get 0.5, prediction 0.5 है। Negative पे 0 है, it slowly rises and then it goes to 1. तो जब when theta transpose x is greater than 0 which means कि somewhere here, तो आपकी prediction 0.5 से, this is 0.5 से increase कर रही है। तो 0.5 से इंक्रीज कर रही है, इट मीन कि यू गोइंग टू असाइन इट द क्लास 1, लेकिन यहाँ आपका जो ग्राउंड ट्रूथ है वो तो क्लास 0 असाइन कर रहा है। तो इट मीन्स कि जो ब्लू वन विल मेक अ रॉन्ग प्रिडिक्शन। सिमिलरली ब्लू वन इज गोइंग टू मेक दीज टू 0 ऑल्दो दे शुड बी 1। तो इसलिए इस केस में द येलो इज द राइट पैरामीटर, द राइट हाइपोथेसिस। Okay, is this clear to all?
Yes, sir.
Any other question? Because I'm not going to cover the cost function in today's lecture. So this is the last slide. Any question? Please ask now. Okay, any question, please? ठीक है, तो आई होप कि सबको समझ आ रहा है एंड वी मे हैव अ क्विज टुमारो। आज हमें टाइम नहीं मिला। प्लीज़ गो थ्रू दिस linear regression, logistic regression, and also go through the example that we did in the previous in the first part of the lecture, and also go through this OHT1 sample. It contains different questions related to the topics that we have covered so far, and so I mean, if you do them by yourself, you should be able to do the OHT1. If there is no question, then we can finish the lecture.